All right, so let's see what's going to be on your Unit 2 exam. Right now, I've got the review sheet out, and I'm going to try to make sure that I hit everything. But, oh, I try. So, one of the terms I think you might run into is planetesimal. Let's see if I can do this and this. Okay, cute little planetesimals. Those are kind of the precursors to what ultimately became planets. Sounds like planets. In Also, I have on my sheet, you're going to want to be able to compare the terrestrial planets and the Jovian planets, and I really like this. Of course, the terrestrials are rocky, high density. They don't generally have moons. They're closer to the sun. They're made of metals and rock. And then Jovian planets are larger. They're gaseous, so they're low density. This is the gases. You can't stand on them. All the Jovian planets have rings and moons, and they're farther from the sun, and they're cold in general. The tops of the planet is cold. I also then have on the review sheet that you need to probably know the term. I didn't have galactic recycling, but I do have on your review sheet solar nebula. So solar nebula was the kind of the mess of stuff that ultimately became our sun and the planets. And then also I have in the review sheet, you need to know the general process by which our solar system formed. The solar system, of course, is the sun and the planets. So it started out with the solar nebula. We have some more terms coming up to kind of describe what that looked like. Let's see what else we got. Yeah, this is to me the slide that if you're looking at how did our solar system form, this is kind of it. This would be the solar nebula, SN, solar nebula. And it began contracting. So the thing in the middle became our sun. It got hot right here. Okay, this material then actually, the word is accrete. It's coming up on another slide, accretion. The material kind of snowballed together. We have these planetesimals. So you know the way our solar system formed. Frost line is the line between, I'll put M for Mars and J for Jupiter. So the frost line kind of separates the last terrestrial and the first gaseous planet. So it's the point at which kind of the gases and things out here would go ahead and condense or solidify, but closer to the sun they would not. Let's see, the term accretion I have right here. Accretion is just talking about kind of the snowballing process of the stuff in kind of an orbit getting large enough to become a planet. I also see a term on your review sheet here, um, protoplanetary disks. And so this is actually, I believe, is taken in Orion. Yeah, Orion Nebula. So basically, we have a little budding. It's not quite a star, so but I'm going to make a symbol of a star. It's a protostar. It hasn't turned on, and this is the material around that star that's going to make a planet. So protoplanetary disk means it's kind of that material like happened in our solar system that can make planets around a budding star. And this is still protoplanetary disks. So these are all kind of different budding stars and their planetary systems in the important region in Orion. Let's see. I'm going to have a question on there about this. So this here's our sun, and this would be the protoplanetary disk. There's our disk that's going to make the planets. And then if we make this Jupiter, this is kind of a look at Jupiter close up. So Jupiter, you would tell me, has lots of moons, and the reason is kind of well related to the formation of Jupiter. It had kind of a swirling disk around it that made lots of those moons. But not all moons were made that way. Some moons were captured. So I've got a question here. I'm going to ask you some dates, and one of the years or amount of years ago, 4.6 billion with a B years ago. Actually, that's when our sun turned on, and our sun turned on. It began what we say creating energy in its core. We're going to be talking more about that in the next unit. But as it turned on, it had this kind of outward going wind. So to me, if you look between this is the sun off. Okay, this is the sun on. So you can kind of see that the sun with its solar wind kind of cleared the plane of the ecliptic, didn't it? Except for the big old planets that were left there. I also have, and this would get, you need to know what each planet looks like. So just general appearance of the planet. Okay. hint, hint, you're going to have to be able to kind of pick them out in a lineup. So that's kind of fun. It's our first planet. We're going to, well, go back. What else do we have? Planetary differentiation. That's like your the heavy things sink and the light things rise as long as a planet is ooey gooey. And as planets started out, they were liquid. So we can have this planetary differentiation. That's why our core of planets have a lot of iron in them. And then the crust has like the lighter stuff. Let's see, which planets have moons? I'm just going to go ahead and let's see, how do I say this? Just know which planets have moons. You guys told me in class, which especially the terrestrial planets have moons. There'll be a question about that on there. Then I have general structure of terrestrial planets and Earth's moons. So we generally have this, crust is on the outside, then followed by the mantle. The lithosphere is the crust and part of the mantle, and then beyond the mantle we have the core. So we have this general thing going on. Now, remember then that they're not necessarily proportionate. Like Mercury has a big old honking core, okay? The Earth and Venus are kind of like sister planets in a sense. They have similar cores and mantles and crust and lithospheres. Then, let's see, how do they compare? Looks like I don't have a question about, remember the pizza? Like this isolated piece of pizza cools down a lot faster than this retains its heat. Let's not have a question about that. All right, caloric basin. So there are certain features of the planets that I'm going to want you to associate. So this is a look at, is this a look at caloric basin? No, this is a look at Mercury. So Mercury looks kind of like the moon. Here's the caloric basin. And it doesn't do it justice. I think in class we looked at some more pictures. So caloric basin is associated with the planet Mercury. Also on Mercury are these scarps. I don't know if you can kind of see these kind of cliff feature. And I'll probably ask a question because actually the moon has scarps, I believe so. And the scarps on the moon, scarps on Mercury were both associated with when the planet cooled and solidified. Let's see. Interesting facts about Mercury. I think there'll be a question on your test about Mercury's temperature. So it has some crazy hot daytime temperatures and some crazy cool nighttime temperatures. And to me, there's two reasons for that. One is that Mercury is really slow to rotate, and the other is that Mercury basically has minimal atmosphere, so it doesn't have a blanket. All right, on to the next part. So the way that we know, this is Venus. I'll put a V for Venus. And of course, Venus is shrouded in clouds. And the reason we know the surface features of Venus actually just has to do with using radar to map it. Let's see, what else do I have? Oh, so some features on the surface of Venus. So this is Miss Piggy. I don't know if you can kind of see it. So that's kind of how those kind of flat volcanoes were made. I think it was this semester it finally struck me that Venus, it's got that crazy pressure on the surface. So things like volcanoes, they couldn't get very big because of the pressure that Venus has compared to the Earth. So the Venusian, or the atmosphere of Venus, looks like this. And in my notes, I have, there's lots of carbon dioxide. And the carbon dioxide came from burps, volcano burps from the interior of the planet over time. But another thing is that Venus, in its clouds, it actually is sulfuric acid. So H2SO4 is the formula for sulfuric acid. So I'll go ahead and put sulfuric acid clouds. All right. Greenhouse effect, there'll be a question about that. So it's on the next slide. This is again looking at Venus's atmosphere. So it's mostly carbon dioxide. Yeah, it was a 96% carbon dioxide. And this isn't on the test, but remember, it's just hot everywhere, daytime, nighttime. Here's the word sulfuric acid. So here's a look at kind of the greenhouse effect on Venus, and this actually happens on the Earth too, and it has to do with kind of what's in the atmosphere. So we said that most of its atmosphere it's carbon dioxide. And so actually carbon dioxide is a great at letting sunlight through, and then the sunlight will interact with the surface of Venus, and then it's like, all right, so then it will ooze, kind of like a little heater. It will ooze. This is my thermal radiation. And the thing about CO2 is it blocks outgoing heat. It blocks heat. It interacts with that outgoing thermal energy. And so the light comes in, and the heat can't get out. So similar to on Earth. Let's see, retrograde rotation. Retrograde meaning kind of backwards, right? We have a few retrograde things in astronomy. And so retrograde rotation means it's spinning backwards. So if you look down at the North Pole, it's going clockwise instead of counterclockwise. And the reason is we think that it got hit to make this the case. Excuse me. But it's almost a full 180 degree turn, 3 degrees shy of that. So it's really upside down. Okay, and then we go on to Mars, and I only have 3 terms for Mars. Oh my gosh, some semesters are like that. So this is actually Olympus Mons, and I'm pretty sure that this would be, some of you wrote down the video we watched the other day. This is the largest caldera or volcano of a caldera in the universe, actually in our solar system. So Olympus Mons is associated with planet Mars, and it's a very large, kind of like a shield sort of volcano. All right, what else we got? The other thing, and I have several slides to kind of convince you of this. We did this in class, but Mars does not have like flowing water now. But can you kind of see this looks like little river, okay, like tributaries. So that's evidence that Mars used to have flowing liquid water. And this also, you can kind of see the gullies, sort of marks that water used to flow on the planet Mars. And then this is, again, liquid water, proof of liquid water. This one, the caption said that, and I can kind of see this. This used to be like a slab of mud, and then as it dried, it cracked. So the mud would be the liquid water. So I think that's cool. And the last thing I have about Mars is that these are moons that only a planet could love. So these are the moons of Mars, and they look like potatoes, and they were most likely just kind of captured miscellaneous material that has been got too close to Mars and has been orbiting ever since. Then we go on to the Jovians. Okay, and then I have which planet, these are the Jovian planets, gaseous planets, has the fastest moving winds? And your answer is, dun 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 dun, may not be intuitive, but it is Neptune, has the fastest moving winds. So there's the answer to probably a multiple choice question. And I've kind of heard it described, it's actually a little bit of a quandary. There'll be a question on there about how massive is Jupiter. So just kind of the stats on Jupiter. If the Earth, you'd have to take over 300 times the mass of the Earth, and you get Jupiter. Wow. So if you take all of the other planets and make a blob, so Jupiter's still 2.5 times larger than that. The volume-wise, it would contain 1,300 Earths. And Jupiter would have to be 75 times more massive to become a companion star to our sun, which we're going to see that most stars actually have a companion. The thing about Jupiter is this is the Great Red Spot. Okay, so there'll be a question on there about that. This is also the Great Red Spot. Pretty. A storm that's been in doing its thing for about over 300 years. Got evidence somebody saw it back then. Okay, after Jupiter, Saturn. So one of the things about Saturn is this is an artist rendition of the matter in Saturn's rings. So actually the reason it's so beautiful and reflective is because it's icy coated rock, basically. But the thing I want you to know is it's not a solid sheet of material. Then I have a couple of slides here, and I don't know what the question's going to look like, but you're going to need to know the general kind of structure of Saturn's rings. There are 2 major divisions. We have the Cassini division. That's the one, as I understand it, we see through our telescope most likely. There's an Encke gap kind of farther out there. So this is, you're going to kind of want to know the structure of the rings of Saturn. So it starts with C, then it goes B, I know it's strange, and then it goes out to A, and then we have a teeny weeny F ring out there. The thing we see through the telescope is Cassini division, and there's the Encke gap within the A ring. So I kind of generally know that. Another cool thing about Saturn, I'm not sure if this is just the southern hemisphere or the southern and the northern hemisphere, but can you see this six-sided hexagonal kind of shape that's in the clouds of Saturn? That is so cool. We go on to Uranus and Neptune, and one of the things about Uranus is you'll usually kind of see its like axis of rotation tilted in the plane of the ecliptic like this. And again, like Venus, it was hit, like Earth, it was hit, and it just has like a 90-degree tilt of this axis of rotation. And see, I also have for Uranus, need to know generally how were the rings of Uranus found, and this is how they were found. So the planet, fortunately for us, is kind of like its axis of rotation lies in the plane of the ecliptic, and its rings then actually extend out of the plane of the ecliptic. So as Earth changes its position orbiting the sun, okay, here's the sun over here, we actually would see a distant star get blocked out by this ring material. So the purple is the ring material of Uranus. And so this is kind of showing the blackout of the distant star. This is by the planet, this is by the rings, okay, as the Earth kind of tootled around orbiting the sun. So that's that. So Uranus, with regard to its seasons, are kind of crazy too. So here's its north axis and here's its south axis. So here, north is in summertime and south is in wintertime. And then over here, of course, its axis of rotation stays tilted in the same direction, just kind of like the Earth does. So now the southern hemisphere is in summer and the northern hemisphere is in winter. So it just has some crazy seasons. So there'll be a question of that on your test. Then we move on to Neptune. What do I have about Neptune? Wow, all I have is how was Neptune discovered? And actually it was related to Uranus. Uranus had some kind of oddness in its orbital pattern, and that oddness was due to the presence of yet another planet beyond Uranus. Then we go on to, on to moons. Okay, so moons know a little bit about Io. So I'm going to pick on Io for this class. So Io is the closest moon to Jupiter that Galileo saw. So Io is one of those 4 Galilean moons. And so the surface of Io looks really pocked and it looks kind of yellow. And actually that yellow is due to the presence of sulfur containing compounds. So I'm going to have a question on there about how is Io get its heating, because it actually is active. It's like got these weird volcanoes. They aren't normal volcanoes. They spew out actually not lava, but kind of gases containing sulfur. And so anyway, the way it is heat gets its heat is by what we call tidal heating. And remember on Earth that the reason Earth has its water, ocean tides, has to do with the moon kind of pulling the water off of Earth. And so related to that, now in this case, a moon is being tidally squished by the presence of, I shouldn't put a star there. This is Jupiter. So it's actually part of it is pulled towards Jupiter. And so actually it kind of has this kind of odd sort of pulling towards Jupiter at different points as it orbits the planet. So it's kind of like a flex ball. And this again is looking at kind of the pockmarks of Io. And so you can kind of see the yellow sulfur containing compounds. And it is a dynamic situation because it has these little weird volcanoes kind of spewing that material. Then I think what I'm going to do is, Titan I might ask a few questions about. So Titan actually is the largest moon associated with Saturn, and it is, I think, the only moon to have an atmosphere. Okay, so Titan is the only moon to have an atmosphere. It, kind of like Venus, has a kind of clouds that cover it. And about Titan. Okay, so there'll be a question about Titan. And this slide's about Titan. This then is also a moon that orbits Saturn. This is the cool one with the tiger stripes. So Enceladus, and I think I have it on the next slide, Enceladus is one of several moons that we think underneath the icy crust is liquid water. Actually, we know that for sure because this is kind of what was liquid water kind of shooting out, and as it shoots out, leaves the planet, it solidifies. So we kind of have these snow geysers. How fun is that? And then leaving, I don't think I have one for Uranus, but this is one of Neptune's moons. So this is the one that has kind of the cantaloupe feature, and it's called Triton. Okay, so new Triton, and you guys in class convinced me that that was a reasonable association, the planet Neptune and the moon Triton. All right, then we move on to electromagnetic radiation. So like I've been telling you in class, I should see these guys listed on your card, visible, 7 cousins. So these are the 7 energies of, generally speaking, of electromagnetic radiation. And in my review sheet, I say know the relative wavelengths and frequencies. That's coming up. I think that I'll be able to show you that. So generally know how to draw a wave. So electromagnetic radiation travels through space in what we call a transverse wave. So it goes up and down and up and down. That's why, remember, it can be polarized. Okay. So anyway, so from peak to peak, peaks are called crests. We can actually come up with an important feature of that energy called the wavelength. The bottoms or the dips are called troughs. So you're gonna want to know, I think it's coming up. You're gonna want to know a little bit about, if you heat something up, what happens with regard to its color and how bright it is. What we call the intensity is how bright it is. One is that we talked about this in class. You call that red, orange, yellow. Okay, and this is the longest wavelength, and this is the shortest wavelength color, or well, here anyway, the color here. So basically 2 things: it'll get shorter wavelength as it gets hotter, and then the other thing it will get brighter. Okay, so be able to kind of share that. Let's see, what else do I have? How are absorption spectral lines created? I think I just kind of threw this one in to kind of show you the increase. So we have 3 lines here. This is the coolest, and this is the hottest, and this is actually the sun. Okay, kind of what we call a black body radiation curve of what a star that's 6,000 Kelvin on the surface, like the sun is, what it would look like. So notice that how high the line is its intensity. So something that's very hot is going to have high intensity. Something that's cooler is going to have a low intensity. And the other thing, and you guys told me this in lecture, is where is the peak? So here the peak is actually going to be even shorter wavelength than the shortest color of light visible. And here, down here, the peak is going to be actually on the other side of red, infrared. So those 2 things. But so I see that I don't, in my review sheet, have any place where I remind you how this works. So these are short, and the symbol for wavelength is this. It's like a letter A, right, with a hat. Short wavelength, and these are long wavelengths. And then the other thing is, I have in my notes, you're going to need to know what frequency is, how frequency is related to these 7 cousins. And as it turns out, these are high frequencies, short wavelength, and I'll put a little letter F for frequency, and these are low frequencies. So kind of review that if you want. Or frequency, remember, is where I said you're counting cycles as they pass you. So frequencies is cycles per second. Let's see. I think that I already kind of said this stuff. Okay. I don't know where I'm going to. Okay. Just be able to describe them. Wow. I'm going to. That. Now, I have something about how are absorption and emission spectral lines created. So it'd probably be 2 questions. One is that it's all about the electrons that are going up to a higher energy level or going down to a lower energy level. And then the other thing is we talked about 2 types of spectral lines. These actually, I can see by the arrow kind of pointing down like that, these are all going to give us actually emit energy as they fall from a high to a low energy levels. So they are going to emit energy. These are going to give us our bright line. And remember, like we saw actually those are the ones that we saw at the end of class on Wednesday, with kind of those little squares that you held up to look at the zzz lights that were glowing. So it's characteristic of which element it is will give you a different set of these lines, these spectral lines. So what I just showed you, what we just saw, where excited electrons are going back down to the inner lower energy levels, will give us these bright line spectra. These are sometimes called emission lines. Now, if you're taking a test and I forget to kind of use both terms, that might be a thing you can ask me about. I'm not sure. The other type of situation is where the same element will give us these what we call dark lines, and that is if this is my nucleus of my atom, and here's where the electrons can be with regard to energy. So absorption lines or our dark lines are created as energy is taken by the electron to go up. Okay, so these will create our dark lines. Okay, so sometimes these are called absorption. Yeah, we do that in science. Sometimes we have like the different words for the same thing. Arrgh. All right. So the last thing in that part I want you to know is this thing about the Doppler effect or Doppler shift. And if something is creating or putting out a signal and it's moving towards you, the wavelengths of that signal are going to be shortened. They're going to be squished together, and you're going to get a kind of what we call a blue shift. If the thing that's emitting the signal, the sound or the light, is going away from you, you're going to get a red shift. And this is, I didn't get these all deleted, but it trains in what we, example of that. All right. So let's see. 2 types of telescopes. Goodness, did I not have that? Oh well. 2 types of telescopes. I'll do it on these next 2 slides. I'll do these 2 together. One type of telescope uses lenses, and they are called a refractor. Refracting telescope. I'll put T for telescope. Sometimes called a refractor, a refracting telescope. It's the same thing. So in my review sheet, I told you be able to kind of show a diagram of what that would look like. And so here we have light coming in. Okay, here is our lens, and it happens to be a double convex lens, and it will gather the light. It's really similar to, and I'll probably say this in lecture, we haven't covered this in lecture yet, it's similar to a magnifying glass. It's exactly the same thing. If you have the sun up here, of course we wouldn't do the sun telescope usually. But the light is gathered to a focal point, and then this is actually, then we can take this and kind of unpack it to an eyepiece. So that's with a refracting telescope. And the second type of telescope uses mirrors, and so here's a mirror down here, and we call it a reflecting telescope. Sometimes called just simply a reflector. Now, my favorite, if I had to do this for a test, hint, hint, I would choose this one right here to kind of show a diagram. This is like the one that I had out recently at a lab. So basically we have light coming down, and I'll show you this in class. We have light coming down to this mirror, and this mirror, notice it's not, it's what we call a concave shape. Actually, it's supposed to be parabolic, but concave is close enough usually. And so the light comes down to the mirror, and then notice that the light comes down and it bounces off, and it bounces to what we call a secondary mirror. I'll just put second mirror. And the second mirror actually is flat, but it's at an angle, and it will shoot the image out here. So this is where we view the image. Here's my eye. Okay. So that's what we call a reflecting telescope. There's this kind of different types of reflecting telescopes, but that's a real common one called a Newtonian design. So it looks like I am going to, oh man, you're going to have to look it up. I see that I missed, make sure you look up angular resolution. Angular resolution. look it up in my notes, probably a vocab word. And angular resolution is about kind of how much detail can you see through a telescope. Then there'll be another question about adaptive optics. Adaptive optics, I just think that's so cool. Read about it, and it's where adaptation means that you're actually getting input and kind of changing what you're doing or how you are. And so adaptive optics, the mirror actually changes shapes. I think that is so cool based upon what the sensor is sensing that the atmosphere is doing. And then I have interferometry, and interferometry just sounds like, it is just so cool because it takes multiple telescopes, I'll put T for telescopes, and they combine a signal into one. So, and the reason we have to use interferometry for to look at objects at those long wavelengths, like radio wavelengths, just because the wavelength is so darn big. So interferometry is really helpful, especially for those long wavelengths. And then the last one I chose was Twinkle, Twinkle, Little Star. Okay, so twinkling actually, some people say planets don't twinkle and stars do twinkle, and there is something to that. So the reason stars twinkle has to do with the Earth's atmosphere. So sometimes they'll twinkle more than others. And twinkling is caused by chunks of air moving in the upper atmosphere. I guess it wouldn't have to be upper, but and with the different temperatures of these chunks of air alternating warm, cold, it actually makes the light from the star look like it's dancing. It's coming here, then it's coming here, it's coming here. It's called refraction, actually, similar to what our lens does to light. So twinkling is very, if you've ever like gazed at a flame, an open flame, like this is your candle, here's your wick and here's your flame. Goodness. And you look up here, actually the image up here or whatever you're looking behind looks kind of wavy. That's twinkling, that's refraction. Well, I think that's it. So let me know if you have any questions. I hope this helped.